Okay, so as we keep going through here, they're kind of talking about what these different fields are used for. So I think you all went through this different stuff. I kind of mentioned earlier that, this is this is the command. This is your first input. This is your second input, and this is your output register. Flip through this. We've already done a bunch of hexadecimal conversion stuff, so we're good at that. Decimal binary hex. This was that little 4-bit trick, right, that we looked at. Yeah, so here's the breakdown. So our opcode, this is the unique code associated with in that 11 bits. The second register source, so this is a source operand. This is number of bits to shift, which isn't used in add, but it's used in some other things. We'll talk about bitwise shifts today. And then the source operand, this is the first one. So this is actually 1, 2, and then destination. Okay. All right, so this is kind of what we were just talking about. How do we translate assembly language into machine language? So kind of that steps what the compiler is actually doing. So if we had something in a high level language, like we're going to set, this is like an array, right? So some array at position 30. So if we're thinking about this in like a C, we're saying go to memory address A plus 30 and set it equal to something, right? So the command we're looking at is A30 is equal to H plus A30 plus 1. So let me just copy that directly. It's equal to H plus A30 plus 1. Is that it? Yep, so this could be like your C code. So what we're actually doing is we're saying store into this memory location H plus the value that currently lives in that memory location plus a 1. Okay, so that's the thing that we are trying to convert into low-level language, in this case, the LEG V8 language. All right, so if you put yourself in the kind of the role of the compiler, this goes back to that slide where we said, how do compilers work? We have to think about if we're writing a compiler, how do we convert something that effectively is this? I've rewritten this to be this. That way we're focusing on the memory aspect of this, because that's going to give us when we deal with loads and stores, that's going to give us a good idea of how this is going to end up getting placed. So I just rewrote the syntax just a little bit here. How would this translate into functionally equivalent low-level language? All right, so we know we're ultimately going to be storing something in this memory address. Okay, that's where it's ultimately going to go. So if we look at their example here, so we're going to load into X9, so one of their registers, and we're going to load in there the value of, did they already put into X10 the base address? Yeah, X10 has the base address of the array A. So they give you a little given information. So you've already have the base address of A inside of X10. So we're going to put inside of X9 the value that currently lives in X10 plus 240. Where's the 240 coming from? Is that size of something? 230 yeah, 8 bits. So it's a bite-sized chunks. So this is an offset of 30 bytes, right? So that's going to be 240, a step of 240 bits, okay, or 30 bytes. So we'll load into X9 that value. Then we will add whatever's in x21. Actually, this is going to be the x21 corresponds to h. So we've already loaded h into x21. I wonder why they didn't show those two lines here. They just gave it to it in text. All right, so they've told us the base address is in x10. The value of h is in x21. All right, so we start off by putting into x9 a at bucket 30. Then we're going to update x9 to be h plus what was that? A at bucket 30. All right, so now x9 now holds the sum of x21 and x9. Actually, it's the other way around. It's x9. This is the destination, right? I believe that's the destination. So make sure I'm telling it to you correctly. Yeah, the last one's the destination. So we are going to store into x9 the current value of x9 plus the current value of x21. And actually the order that it's going to happen in is the current value of x21 plus the current value of x9 is going to get stored into x9.
Yeah, I think the first one.
I don't think so. That's not the way they're showing it here.
That's what I was doing when we were doing exercises. That's what I had set up.
Because here's add. Oh, so maybe this is how they're storing it, but not necessarily how the function's working.
Right. Yeah.
Okay, I get it. All right, so store in x9, x21 plus x9. So this is h plus a at bucket 30. So we've overwritten 9 with that. So now we've done the plus h part. Now we're going to add an immediate value. So we need to use add I in order to give ourselves a literal, to do add an immediate literal. So x9 will equal whatever it's currently equal. What it's currently equal is a30 plus h. Now we're going to add the 1 onto it, storing the result in x9. Then finally, we're going to store into this memory location. So this is the destination in this case. This is the destination in this place, definitely. Because we're taking the value x9, whatever lives in there, which is our sum, right? x9 currently holds h plus a30 plus 1. And we're storing that into this memory location. The base address of a, which is an x10 plus 30 bytes. Does that make sense? All right, so these 4 lines are equivalent to this 1 line. So think about if you had to, and we can make an argument whether this was the right order to do stuff. Like, would it have mattered if I had put, maybe added, putting into x9 the current value of h first? Could I have done these in a different order and still gotten the same answer? I could have said h first and then h plus 1 and then gotten the value of a30 and then ultimately stored it back. So if you're writing this generically, if you're thinking about this code, and you're putting yourself in the shoes of the writer of the compiler, how do you break that down? Because you need to write something generically, right? You're writing a generic tool that will take something that looks like this and turn it into those 4 or 5 instructions. How would you do that? Well, you're making a pass through this, so you're reading it in kind of line by line, right? So if you read in a line that looks like this, your job is now to convert that high-level line into equivalent low-level code, right? We're not going to think too far ahead of ourselves. We're going to pretend like in our little program right now we only have 1 line of code to keep our life relatively easy. So now we're going to say, okay, well, how do I generically handle that and turn it into a bunch of stuff? How many steps am I going to need? When I look at this, I see 2 plus signs over here, right? So I'm going to have to do 2 adds. All right. And then we're going to have to ask ourselves, so if we kind of walk through this, as we're walking through this, so I'm looking at everything before that equal sign, correct? So I'm trying to decide which kind of expression am I looking at, or in this case, it's a statement. So I happen to be looking at an assignment statement, right? So we would probably classify this guy. We would read it in, we'd kind of do a pattern matching thing to look what kind of statement are we looking at, and we'd probably say that this guy is an assignment statement, something along those lines. All right, and we would say that the assignment statement, the generic format of the assignment statement is going to be destination followed by an equal sign followed by an expression. Make sense? Okay. So then we're going to say, okay, well, what's my destination? That part's easy. We can bring out, well, high level, it's easy. So we'll say that's where I'm storing, ultimately going to store stuff here. Now I need to look at my expression. So we need to decide what kind of expression is this. This is an arithmetic expression, right? So we're dealing with an arithmetic expression. So that's what this expression is here. It's an arithmetic expression. And what is the general syntax for an arithmetic expression? It's going to be expression followed by op followed by expression. You might call it a math op or something like that. Okay? So the left-hand side here, that kind of expression is going to be maybe a var expression. So that guy's a variable expression. And then the operator I found was a plus. And then what's on the other side of it is another arithmetic expression. And that arithmetic expression we expect to look like an expression plus an op plus an expression. And in this particular case, it's going to be let's just call it a var expression again. It's actually going to be reading it from memory, but it might as well be a variable. So this is a var expression followed by the operator plus, followed by a lit expression in this case. So found a 1. That makes sense? Okay, so it's broken down. At this point, we've done a whole bunch of identification. We said, okay, I see this, I see this, I see this, I see this. This is what I'm expecting. So I looked at the entire thing, okay, and just decided, okay, this is a assignment statement. We're assigning the value to the thing on the left-hand side of the assignment operator. Great, so what does that look like? It looks like destination equals expression. All right, so what does destination look like? Destination is just a place. So in this case, we're going to call this guy, we'll call it a var expression just for simplicity right now. So then what's going to be on the right-hand side of that is going to be some expression. So now we look at this expression over here. We look at the rest of the stuff here, and we try to identify what kind of expression it is. Do pattern matching stuff. We decide, it's an arithmetic expression. So what's an arithmetic expression? It's an expression followed by an operator followed by an expression. So the first expression I find is the expression that is h. That's a var expression. Then I find my operator, which is a plus. Then I find another expression. So I find another expression. This particular expression is an arithmetic expression. What's an arithmetic expression? It's an expression followed by an op, followed by an expression. So I can try to get my first expression. My first expression is this var expression, followed by my op, which is a plus sign, followed by the number 1, which is a literal expression. That makes sense? So now I've generically identified the pieces of that line. Given that, can I create a framework for what my one-line instructions might look like? My individual little, kind of glance back here. We see we had to put something into a location. So we had to start it off and be able to do some math. So we had to pick a register. Now, if we think about this in the big scheme of things, we have to solve problems in terms of the tools that we have available to us. Well, in ARM, we have 32 registers available to us, right? But not all of those 32 registers are general purpose. Most of them are. I think there's like 4 registers that are for other things, but whatever. We also would have to keep track of, if we're a real compiler here, we'd also have to keep track of which registers are we already using for other things. Make sense? So we have to pick currently unused registers. That way we're not overwriting our own stuff. All right, so let's assume we've gone through the motions and recognize that X9 is fine, and the registers we're picking here are going to be reasonable. All right, well, before anything else can happen here, the presumption is that, and the reason why they have told us here that X10 is the base address of A and X21 is the value of H. Why didn't they show that here? What is this stuff? That stuff there is the result of converting this into low-level code. But A and H were defined before this line somewhere, right? So they're just presuming that whenever A30 was defined, or whenever A was defined, it then had some assembly language associated with it that ultimately threw into X10 the base address of A. And then also you would have had a variable defined somewhere called H, and it would have put into, in this case, X21, the value associated with H. So that's stuff that would have been further up in our program. That's what they've given it to us here. Okay? So assuming we already have that information and that's available to us, we want to ask ourselves, how did we go? Let's just think about this, the right-hand side. So these are arithmetic expressions. Because notice we're doing an add here and an add immediate here. So we have 2 adds. And when we come back here, we also see we have 2 plus signs. 2 arithmetic expressions translated into 2 adds. We know that for one of our adds here, let's deal with this, this first one. We have, actually, the way this probably would have happened, so let's break this down. Because look at what they did first. They loaded A30 into X9. Right? Then they added X9 plus H. So they did this step. They did this plus this first. Okay? So what they did is, as they were processing this, they ran into their var expression. And that var expression happened to, we had previously known that X21 held the value of H. So, but rather than loading H in immediately, they looked at the next part of the arithmetic expression. So they're saying, okay, I'm gonna need that somewhere. I already have H stored, so I don't need to store it again. Then I'm gonna hit the plus. What does the plus say that I'm gonna be doing? I'm gonna be doing some addition. But before I can do that addition, I need to look at the other player in this addition. The other player was an arithmetic expression, and the first part of that was an expression that was a var expression. Okay, and that var expression is a memory address. So this A30 further defines that memory address. All right, so since I've detected that A is a memory address, A is an array, when I go and I look up the base address of A, I then need to find out where A30 is off of that base address, and I need to put it somewhere. So the very first thing they've done is they've given us a convenient way of using bucket 30 of that array. So they said, okay, well, we need to get that, so we're going to go ahead and load into a register. They just picked a register that was available, so we'll load into X9 that value. Okay, that's our starting place, because we already had X21. We didn't have to load H. That's already in a register. All right, if it hadn't been, we would have had another load instruction in there. We would have 2 different loads. We would have loaded the left half and loaded the right half. All right, so we already have this left half, so we don't need to worry about that. We know we're doing some addition. We're going to then load the right half so I can do my addition. So this guy right here is a 2-step move. Load the appropriate memory, then perform the add. And we're doing a normal add because both sides are var expressions, let's say. Neither side's a literal. All right? So that's where these first two lines come from. Load my memory address, do my adding, keeping the value in x9. How did we know that it was okay to keep the value in x9? Why didn't they pick, x10 and stuff like that to store extra stuff? I mean, it makes sense to keep it small.
We don't need x9 to retain the value of x9.
Why? How do you know that?
I mean, we are not assigning back to h here.
Well, x9 is currently holding the value it lives at A30.
You only use A30 once. Like if A30 was in that expression more than once, then you might use X9 more than once.
Okay.
Like if it was A30 plus A30, I don't know.
What's the question?
How do we know that we're able to store the result in x9 here, rather than having to move on and actually store the result of x21 and x9 into like x10? Why do we know that it's safe to overwrite the value of x9? This high level.
We are about to change the.
Say this again.
We are about to change the A30 value.
Yeah.
So we are adding everything into it. That's fine.
So all the stuff we're doing down here, all that stuff right there, that's all us. That's all our partial steps to solve this side of the assignment operator, right? We're not following anybody else's rules here. We don't need to worry about us needing this value again in a second because we are incrementally solving that problem. We are controlling that side of the problem, okay? So we've broken this thing, this side up here, into multiple small steps. All right, so we decided how many steps do we need? Well, we need a memory location for this guy. Already had it. We need a memory location for this specific guy. Although we could have, I'm guessing add I for add immediate won't do a memory lookup, so that must only work for literals. So I was going to say you didn't actually have to load this into, you could have done this in Intel. You didn't have to load this into a memory address. You could have grabbed it immediately from memory. But I'm guessing ARM can't do that. So we already have this guy in a register that was given to us. This guy's a literal. We don't need to load him anywhere. So the only thing out of these that we need to load anywhere is this value. So that's why we did that first. We loaded it into x9. And then we go ahead and use that single variable as our accumulator. So we add on to that the h, overwriting the x9. Why are we safe to do that? Because we're just in the process of calculating what's over here. We're still working on one line of code. Right? Lots of steps for one line of code, but we're still working on one line of code. So we completely control this situation here. So we can reuse any variable that we want as long as we don't overwrite a value we're going to need in a minute. We know this is going to be an add immediate because the last part is a lit. So if we go through and we read this, our first thing is going to be an add because we have a var expression and a var expression. So that's going to be a normal add. So after we get everything into memory so we can work with it, we already have h in memory. So we've kind of checked this guy off the list. This guy's not in memory, so we loaded him into memory. So that was the first thing we did. So we did loads and then we did the mathy stuff, right? So we loaded this guy into memory so we can work with them. And we picked x9 because that was available, let's say. This guy doesn't need to get loaded into memory. He's a literal. He's just available to us. So as we went through and we identified this, we said, okay, the first thing we're going to do is we're going to do addition. In the left and right hand side, this is a var expression. This is a var expression. So add those two guys together, producing an answer stored into x9. Var expression plus var expressions, overwrite x9 with that. Okay? So now, these two guys, that's been complete. That first add's been complete. The answer's in x9. So now I'm going to do another add. Well, what kind of add is this? Well, the left-hand side is a var expression. The right-hand side is a literal. So this is an add immediate. So I'm going to perform that math, storing the result back in X9, which we know we can use because we're still in the one line of code. All right, so our final answer in X9 is all that crap. Okay, finally, the last thing we're doing here, because this whole thing that we're looking at is an assignment statement, which says after I've done all my mathy stuff from the right-hand side, this arithmetic expression, I need to ultimately stick the result back into my destination, which is a var expression. So a memory location. So to put things, so now we're talking about resource management. This is RAM, correct? This is RAM, correct? When we need to get stuff, this is system memory. So like your 8 gigs of RAM, your 16 gigs of RAM, that kind of stuff. So that's one of our resources in our system, in our computer. When we need to bring something from system memory into local memory, into a register, we load it. When we need to get something from a register into system memory, we store it. So those are our tools, those are our magic tricks for communicating with system memory and registers. That make sense? All right. So, and then the mathy stuff in the middle has to do with those magic tricks. So an add immediate can operate a little bit quicker because this is a literal value. Like the value of 1 is not a changeable thing. Like next week, a 1 isn't just going to be a 4. So it's a thing. All right. So so add immediate versus add. This guy is probably a quicker instruction. Probably. Still a single magic trick, but we'll talk later about atomic instructions. This guy would not be an atomic instruction because we will have to resolve the value of X9. So this will take at least 2 cycles, but whatever. It's likely going to be faster because up here I have to resolve, add, and put the result here. Down here I have to resolve, then add, and put the result there. So I'm at least one less step. A little bit quicker. So they decided, hey, to give some performance benefit to this, since I have room on the chip and I have room in my 11-bit op space, I'm not at 2048 instructions yet, I'll go ahead and give myself an add-I. I found a nice little corner there in the chip and made my little procedure for add-I out of my copper wires that they then brought down into a printed circuit, very large scale integration stuff. And that's going to be a really fast little magic trick for adding an immediate value. That's something we do pretty often. That might be beneficial. That's why we have 2 different ways of adding. All right. So, but the important thing for us here is to recognize that resource management stuff. When I need to bring RAM into a register, we load. When I need to bring a register into RAM, we store. Make sense? All right. Yeah, see here they're referencing MIPS, and I think there's some stuff later on for like real world stuff that talks about MIPS as well. But this is also a reduced instruction set type thing. Unlike MIPS, the leg V8 immediate field in I format is 0 extended. Thus, leg 8 includes both add-I and sub-I instructions, while MIPS has just add-I and both positive and negative immediates. Okay, so they do. So MIPS does adding with adding and subtraction with just adding for add immediates, and it does where leg V8 does adding and subtraction with 2 separate functions. Good question? Oh, all right. So skip through the rest of the stuff. We think we pretty much. That's interesting. Why did they say 10 bits here? Oh, because this is an I format. Unimportant. All right, so they're showing you some of the different things here. They have this R versus I versus D format. So notice that our loads and stores when we're going to real memory, these are D format codes, so they kind of show you how this actually works. Our immediate stuff are I format, and then our register stuff is going to be R format. All right, so just at the end of the day, it doesn't necessarily matter unless you're the one writing the low-level code for how the stuff is actually stored. From our perspective, we just want to understand that it's stored. Okay, I think we've talked about the big picture stuff there. That's fine. That's fine. Okay. So now we're going to talk about the shifty things. This is 2.6, so you did read about this, right? Okay. So these are actually operators that you've had access to in other high-level languages. So like the Java operator left shift or the Java operator right shift. What do these guys actually do? So let's look at, we're going to call these guys Bitwise Shifts. So let's say that I have, we'll represent this as 8 bits, the number 4. So this is going to be 1 in the 4's place, 0 in the 2's place, 0 in the 1's place, and then 5 zeros before that. So that's the number 4. Make sense? Now, if we do a left shift on that, left shift says to do what? Okay, so we take every one of these bits and we move it one thing to the left, and then we fill in the new empty spot with a 0. Okay? So left shift of this is going to drop this 0 off. Right? That guy's going to go away. So I'm only going to keep everything after that, and then I'll throw an additional 0 on the end. Okay? And functionally, what has this accomplished? Multiply by 2. So by doing a single shift left, we've multiplied by 2 to the power of 1. Right? If I shift left 3 times, I'm multiplying by 2 to the power of 3. Make sense? All right. So that's our bitwise shifts for doing multiplication. What's a right shift? So a right shift, we're going to move everything to the right. So the thing that's going to drop off is the far right bit there. So we'll keep all that stuff. Drop it there. And we tag another guy on the left-hand side. Okay, so now my 4 just became a 2, so we divided it by 2 to the first power. Make sense? All right, so what's the purpose of shifts? I mean, on one hand, most of you have worked in high-level languages before, right? How many of you have ever used one of the shift operators in a high-level language? Just a couple times, right? Probably for some assignment or something like that. Yeah. It's not something you really stumble upon very often, right? It's there, but we don't really use it very often. Why is it there? Why would I say, let's say I had the number 4. So I say I have A is equal to 4. Well, I can say A left shift 1, and that would give me A 8. Why is that better than saying A times equals 2? Okay, so multiplication is expensive. Why? How does multiplication work in our computers? Just high level. We'll talk about it in detail.
That's like store and call from RAM, or...
Okay, I mean, there's some truth to that. But you mentioned multiplication is expensive. Why is it expensive? And I assume division, you'd say, is expensive as well? Yeah, these are expensive operators. Now, does that mean we never have to do multiplication? We only don't have to do multiplication if what? If we're working with powers of 2. Similarly with division, if we're working with powers of 2. So we can almost think of the bitwise shifts as like shortcuts. So kind of like our conversion when we use nibbles to move from hexadecimal to, to move from binary to hexadecimal and back.
Maybe like we have to multiple adds internally for multiplication.
Yep.
So you need multiple bitwise adds. Instead of that, we just shifting.
Yep. So there would be a bet. So if we make the assumption that multiplication is expensive, and we make the assumption that division is expensive, then using shifts when we have something that's a power of 2 would give us a performance benefit, correct? How often are we working with powers of 2 in a low-level language? Often, right? So not only does it make certain things faster, the very specific things faster, we also are quite often working with powers of 2 because we're kind of working with things pretty close to the binary level there. So it actually benefits us more often than we might otherwise think. All right. Plus, if we think about this, if we're multiplying by shifting left or dividing by shifting right, let's assume we were implementing that. All right. So you mentioned before that we have a situation where we have a multiplication and division would be hard to implement. So we're equating with being expensive operations to being hard to implement. Well, if we were doing a bitwise shift, would that be very difficult to implement? It's a string. I mean, you could store it in an array or something. I stored an array of ints, but only give you enough memory for bits. But assuming we gave us enough memory space, what do? We just move everything over and add and overwrite what's on the far side. Not really a huge deal. It's a little bit of logic, right? Quick little for loop kind of shifts everything over. We're not having to really think about mathy stuff, are we? It's almost like a magic trick. It's like, oh, if I do this, I just multiplied by 2. Okay? If I do this, I multiply by 8. You shift it extra. And we can actually multiply by, we could multiply 8 by shifting left 1, then shifting left 1, then shifting left 1, or we could just shift left 3. So now it's just as fast. We just moved it farther, right? It had to fill in a little bit more at the end. So we actually get even more benefit by using the power tool to its greatest efficiency. And we don't even have to think about math. It's almost accidental that shifting left does multiplication and shifting right does division. So it's a trick. All because we're operating with binary. Right, so is this pretty similar to our conversion from octal to binary and binary to octal, or a conversion from hexadecimal to binary and binary to hexadecimal? It's the same type of thing, right? Because of the nature of how we're storing our values, those moves are very convenient moves. So we should use shifts whenever we can. Okay? Now, you're going to have some situations, and I'm sure we'll see some in a few minutes probably, where you might be on the fence, because there's obviously going to be operations here for multiplication and division, right? That, as you pointed out, are expensive, so we want to use those sparingly, but we still need them. Because sometimes you're not multiplying by a power of 2. But there's some tricks you can do there. You can decide, okay, well, if I have to multiply something, and I can break it down into multiple powers of 2, I can do shifts on part of it, and then shifts on another part of it, and then bring those two things back together to at least minimize the number of multiplications, or as you point out, the number of adds that have to occur underneath the hood for a multiplication. Because 3 times 2 is what? Well, 3 times 3 is adding 3 to itself 3 times. So multiplication at the simplest form, we have this idea of something called fast multiplication, which we'll talk about. But At its simplest form, multiplication is a instruction of a whole bunch of adds. It's repetition of adds is what multiplication ends up being, which the more you're adding, the more expensive it is, right? Okay. So bitwise shifts, no big deal, but we kind of understand the purpose for them, right? Okay, so it's a special move, right? All right, so now bit by bit ands, ors, or nots. All right, so this becomes interesting. And again, so if you're operating in a language, so let's, because this is a bug that some beginning programmers have run into before. So let's call these Boolean operators. If you're learning Java or you're learning C or C++, that guy is the AND operator, right? This guy is the OR operator. And the XOR operator is that, right? That's XOR. What's that guy? This is bitwise AND. Have any of you ever, well, how many of you have ever used a bitwise AND in one of your high-level programs? On purpose. Have you ever, more probably when you were a beginning programmer, accidentally put a single ampersand as opposed to a double ampersand and got very strange results and had no idea why you got strange results? Because it was doing a bitwise AND operation versus a Boolean AND on the full value. Bitwise OR is that. And then, oh, they're not showing you, they're showing you a bitwise not the bitwise XOR. So forget about the not for a second. So this is how you do you might not be able to do a bitwise XOR in Java or C. What's the, you know what the symbol is? Yeah, this is not bitwise though. This is bitwise. What's the full XOR?
I don't think we have it. Do we have any purpose for put of XOR?
Probably not. Well, not that couldn't be replaced with ands and ors. You probably come up with something weird that would benefit from it, but you can always replace it. I just assumed they would have a, no, whatever. All right, so we have this bitwise and bitwise OR. So let's look at these guys. So these are more bitwise operations. All right, so when we're using a bitwise, I'm just going to use nibbles here. So I'll have 1, 0, 1, 1, and 0, 1, 1, 1, something like that. If we're doing a, well, I'll just say and. This is a bitwise and. We're going to say 1 and 1 is 1. 1 and 1 is 1. 0 and 1, that's true and false. That's going to be false. 1 and 0 is false. So this is going to give us the result of a bitwise AND on these two values. So bitwise ANDs take two numbers and produce a number. Make sense? An OR, one says that there's at least one 1. So 1 or 1 is 1. 1 or 1 is 1. 0 or 1 is 1. 1 or 0 is 1. Make sense? Okay. And if we happen to be doing a XOR on this, just because I happen to write it, that means exactly 1, 1. So 1 XOR 1 would be a 0. 1 XOR 1 would be a 0. 0 XOR 1 is a 1. 1 XOR 0 is a 1. Make sense? All right. Why? Why do we have bitwise operations? Why do we have bitwise ands and ors and forget about XORs right now? What's the purpose? What do we use a bitwise and for?
Bitwise and
Yeah.
Usually clear the rest of the string.
for example, addition of two numbers.
Addition of two numbers?
Internally, it should use some kind of XOR sign.
Okay, as part of that step. Okay. Now you were mentioning something about
I'm trying to remember. Some of the homework we did somewhere where we inserted a block of ones at the back or something, and we cleared the front numbers there. So you can kind of manipulate what the rest of the string looks like by using conditions like this.
okay. So again, does it fall into the similar category of a trick?
Yeah.
Same kind of stuff. It's where we are using bitwise operations to manipulate binary strings to get them to ultimately become what we want them to look like, but in a way that is faster, more efficient than doing it the expensive way, something like that. So again, this is only going to work under certain circumstances, right? Now, what about bitwise OR? Bitwise OR has a kind of a pretty common use, actually, in high-level programming. Have any of you ever used the bitwise OR in programming, especially network programming? What's it used for?
Set the bits. I mean, if you do bitwise,
Well, the overall,
set some particular bits. You want to copy some bits.
yeah. So the overall concept is something called masking.
Yeah.
Okay, so we have this concept called masking. All right, and what a lot of times you'll see is you kind of have like almost a code. All right, so when you say, well, I want this guy to have, this option as well as this option and this option and this option. If you bitwise OR those guys together and the original values are specific values, it'll create kind of an encoded solution that has all the correct bits set for that exact scenario options. Okay, so you're kind of, that technique is called masking, to give yourself kind of an encoded string like 0, 1, 0, 1, 1, 1 means that this option is on, this option is off, this option, this option, this option, that kind of stuff. All right, but it allows you to have one value to represent a collection of options, for example. All right, so bitwise or go to move in high level languages. Make sense? All right, and not just flips the bits. So when will we use a bitwise not? Is there a practical use for bitwise not? A 1 becomes a 0 becomes a 1. So bitwise not is not between two numbers, it's between one value, right? We're just going through and we're flipping all the bits in that one value. When would a bitwise not be pretty handy for us? Well, 1's complement, but yeah, on the way to the 2's complement. So that's just one example, but that's the go-to move, right? Just flip them. Now you just add 1 to it, and that's an add immediate, which we already said is fast. So we do a bitwise not followed by an add immediate 1, and that's 2's complement. Easy peasy. All right. So here's the ARM instructions for these. Logical shift left, logical shift right, and immediate. Not sure how the and immediate will work there. I'll have to see here in a second. So they have an and, they have an or, O-R-R, and then E-O-R. I'm not sure what the immediate versions of those are, but I'm sure it'll reveal itself here in a second. Okay, so we've seen how it works. We've gone through these, so they're showing you just, here's the opcode, blah, blah, blah. But notice in this case, they're using that shift space. All right, so they, here's your, the two, in this case. Oh, actually, I guess it would be, now I know what the immediate is. It's kind of stupid. Ands and ors have two values, right? If both values are var expressions, if both values are registers, you would use a normal and or a normal or. If one of the values, if exactly one value is a literal, like a 3, then you would use the and immediate and the or immediate to work with that. Same thing as add and add I. Make sense? It's going to be a higher performance bitwise and if you are working with one of the values as an immediate to use that lesser value because it has to do one less lookup. All right, but we do use this little section that we haven't used before to keep track of the number of shifts that we're doing. Go ahead. Okay, so here, let's just look at an example then. So we'll look at immediate values. So an immediate value is whenever we use a literal, like 1 or 2 or 5, that kind of stuff. All right. So if we want to say x13, is that how? Yeah. Plus x11, we would use an add. If we want to say x13 plus a 2, we would use an add immediate. If we want to say x13, what's that? Logical shift left, x13, x11, we would use a, I'm sorry, I'm giving you the wrong things here. If we want to say we want to and these two guys together, we would use a and, normal and, because both sides are our registers. If we want to and x13 and a 4 together, we would use and I. Similarly, if we were ORing x13 and x11, we would use an OR. For ORing x13 and a 4, we would use a ORI, which is kind of fun to say. ORI. All right. That make sense? So that all has to do with just those immediate values. And it's a performance bump thing. I mean, there's no reason architecturally that you can't perform immediate arithmetic using a single and, or a single add, or a single and. They could make it that way. But that would make that one function slower than either of the individual ones are. So now what they're giving you now is they're giving you a normal and an and immediate. Normal and is faster than the super and with everything encompassed in it would be. And an and immediate would be even faster. So they're giving you two tools that are both faster than that single tool would be. And one of them is going to be, let's call it super fast. And this all comes down to that they have the space to do it, right? I mean, this would have been a little bit different conversation if we had rolled back to the early days of computing when we didn't have a lot of transistors on our CPUs or didn't have transistors. We were still using vacuum tubes or something. We would have had to be very, very, very specific, very careful about what instructions we supported and how we wrote them, because we didn't have a whole lot of space to store the stuff. Where now it's like, we've kind of we're starting to hit our limit on what we can fit onto a single silicon chip. You kind of follow, they mostly talk about it in laptop chips. You'll see it where, it'll talk about like how many nanometers the chip is. That has to do with the way the chip is created. So, if you go back 5 years, the nanometers is larger than the nanometers is today. And what that means is at the microscopic level, if you looked at this chip, it's printing these little copper wires, right? How close can they put those things to each other without them interfering, without them touching each other at the atomic level? Okay, that makes sense? So as our technology has gotten better, we can get them, we can print closer and closer and higher resolution, if you want to think about it like that. But we're starting to bump into some limitations there. That's where they're, talking about silicon having some weaknesses and, well, not weaknesses, but that, we're kind of hitting the end of life for that.
So you think they're going to make the chips bigger or like?
That hasn't been what they've done. They did do that for a period of time. So in the earlier days of Pentium processors, they had a Pentium Pro processor that actually was a physically larger chip.
Yeah.
Didn't really take off.
Couldn't they layer it too? Like, don't they have layers on it? Or?
Yeah, and so part of the issue starts becoming now we're kind of looking at performance versus compatibility. So this goes back to what we talked about earlier. I mean, they could create a chip with zillions of registers on it and zillions of transistors on it, and I think somewhere I read, I think Intel, this actually was years ago, Intel has, a 256 core processor that they're testing or something like that, which isn't practical but they have one. So if you don't have to worry about this thing fitting in some sort of, standardized slot size in a machine, build whatever you want. So now you have to start thinking about, what will fit. Right? So they're kind of playing that game. There's a difference. And that actually really does drive our performance. When we think about our computers, it used to happen every 6 months or so. You'd have almost a double in performance in the early days of kind of personal computers. But the chip sizes did not change. And the reason for that is because we were so far behind what we were capable of doing inside the same space. So we were able to fit more stuff in the exact same square footage for a while. So we could just keep making it faster and faster and faster, and we could use the exact same pinouts on the motherboard. Now, it used to be a lot more difficult. So I think I heard you just built a machine.
Mm-hmm.
All right, so you got, what kind of processors you put in there?
I actually put the i5-86.
Okay, so you took your processor, you just dropped it in, you were done, right? Yeah, it's just zero. So first of all, you have something that we don't even think about anymore. It's a zero insertion force, right? You just drop it in there, it just fell right in, no problem. That wasn't always a thing. So before you had that, you used to have to make sure you had the pins exactly lined up, because you were going to have to apply some pressure to shove it down into those little holes.
Oh my gosh.
Okay. Now, keep in mind that back then, like right now, you look at the bottom of it and you could barely even tell the separation between the pins, right? And back then, you could see the separation for the pins. I mean, if we, here, I'll just show you a 486 DX2. So this guy had a zero insertion force. With a little plastic arm there. I want to see the pinouts on it. Yeah, here we go. Lots of space between these pins. Yeah, so I mean, you can, you would even have a situation where, if you went a couple years before this when they didn't have the zero insertion force, so you would have even less pins than this. Where if you bent a pin, you could get in there with needle nose and kind of straighten it out and kind of hope for the best. Not back then, because the pins were a lot thicker. And now you're screwed, because the pins are like pieces of hair.
The last time I built the computer, like 8 years ago, still have the tiny of a pin on the CPU processor. It literally bent on different way, and I used something to bend it, and I was like, oh my god, I broke it. Literally, I broke it.
Yeah.
the gold pin.
Oh, it's gone off. Yeah, that's not good.
Yeah, the problem.
Yeah, if you start losing physical pins off the processor, that's bad.
But did they start putting the pins on the motherboard? Or is it still the I can't remember.
Well, the processor you just got had pins in the bottom of the processor, right?
I can't remember. I always thought like the pins were
Or was it a magnet thing?
it was on the motherboard and then the processor didn't actually have the pins.
It's possible.
I don't know. I can't remember.
Didn't you just build it like a week ago?
I just built it. Like I can't remember because I didn't look at it. Just like went for it.
Well, but in any case, I mean, it's a different situation today. But what I was actually getting at is, so after you dropped your processor, so forget about the zero insertion force thing, your motherboard just detected the processor, right? That's not the way it used to work. How many of you have ever had to mess with jumpers on a motherboard? Okay, these little tiny pieces of plastic that bridge between two pins. You get in there with little needle-nose pliers, or you kind of use your fingertips, and you'd have to look at the manual to figure out what configuration, because you had a clock multiplier and you had a bus speed. So like a 100 megahertz processor, for instance, back then, might have had a 25 megahertz clock speed with a 4.0 clock multiplier. So you had to do the right math to get it right. Then you can start trying to do some like overclocking. Try to push. This is the early days of overclocking, where you actually got in there and manipulated jumpers on your motherboard. It was a whole different world back then. Now it's all just plug and chug, right? Drop stuff in, turn it on. If it powers up, you got it in right. Good to go.
They have a nitrogen overclock right now.
They have what?
They call it nitrogen overclock. I've heard of that.
Nitrogen overclock?
You can overclock your CPU over 6 gigahertz without over 50 degrees of clock.
Okay.
They have something that holds nitrogen, so basically you have to fill up nitrogen every time something wrong. I don't know. But they have the stuff that holds nitrogen.
I got you.
You just fill up nitrogen in. It's already hooked up.
So you basically have a computer with dry ice in it.
Yep. Actually, the pins are on the motherboard now.
Okay.
They must do that so that way if you do mess it up, you can just replace the motherboard.
Yeah.
Cheaper.
Now, so kind of an interesting thing here, though, is because overclocking is kind of a big deal, right? A lot of people do this overclocking stuff.
Mm-hmm.
Unless you're doing something very, very, very specific. Overclocking has never made much sense to me, since your CPU sits idle most of the time. Yeah. And very rarely is your CPU the bottleneck. So the only place that I really see overclocking as even being like useful today would be like crypto mining, where every little last hash means something, right? That's like, oh, let's just take it to the hilt. But I mean, the rest of the time, I mean, very rarely is your bottleneck going to be your CPU. Yeah. It's typically, if you're a gamer, you have to have a pretty crappy CPU for the CPU to be the problem. Typically, your problem is going to be not enough RAM or a weak GPU, something like that. I mean, the CPU is probably the last thing you want to spend money on. When people are building machines, what I usually recommend, if they're on a budget, if you just have, if the money's a non-issue, just get the best of everything. But I usually, when you were pricing CPUs, you saw that this one to this one was a little jump. This one to this one was a little jump. And then finally you got to one where the next one up was a big jump. Yeah. Get this one.
Well, especially like for the 8th pin, like between the i5 and i7, the benchmarks are like right next to each other. And the price is like $100 difference.
Yeah. Yeah, and I'm not even talking about the benchmarks. I'm talking about the price.
Oh, you're talking price.
Yeah, talking about the price. Where to go from the 2.8 gigahertz to the 3.2, for example, maybe the price is negligible, $50, something like that. But then to jump to the 4 gigahertz one would have been $300.
Yeah. Well, that is why they have a overclock for.
So people can get the lower processor and get the speed of the higher one.
Big jump that equal to $400 CPU.
Yeah.
Like I have i9 798X.
Yeah.
It cost me $2,000 per CPU.
I
can buy the 1,000 CPU and overclock it over, and even though it's better than the one that I have.
Why don't you overclock yours?
Now I overclock. I don't need to overclock this right now, unless they have the new model of overclock. Unless they have a new model of like I-10,
Yeah.
I-11, I will overclock.
Seems like you just get the dry ice thing and overclock it.
Well, I already
Turn
I,
on this
I, I have a tuner, so when I'm overclocked, it's gonna be like 40, 45. Right now, my CPU is really cool. At most is 18 Celsius.
I do kind of have a little bit of a fun story from college. I had a guy who was down the hall from me in the dorms. He or what they call them, residence hall now. You're not allowed to call them dorms, whatever it is. This was back when so he had a Intel Celeron processor, but this is old school Celeron. Like his processor was a 600 megahertz processor,
Okay.
and he was doing something to overclock this thing. And a lot of people who did it big into overclocking, they would use Celerons because Celerons are very overclockable was the idea. So he had this thing at like 2.1 gigahertz or something. He just had multiple fans blowing into his case and stuff. So it was like 3 or 4 in the morning. He's like wakes me up banging on my door. So I'm like all the way at the other end of the hall. I'm by the elevators, and he's at the far end of the hall, farthest from the elevators. He's banging on my door to wake me up. So I come out of the room. I look down the hall, and his entire room is on fire. Okay? There are flames billowing out of this guy's door. Billowing. We're not talking like a little stove fire. His room was on fire. The whole room.
And I got punished for that, like, suspended from school.
I think the whole floor had to pay for the.
Oh, yeah.
Yeah.
Oh,
But I mean, this was not a little damage. This was a total loss of that room. And this was back when the buildings were just all made of concrete. So even the room next to him didn't even get damaged. But his room was uninhabitable. So this dude was sleeping on the floor in my room for like 2 months. You could not live in his room. Even the carpet was crispy. I mean, the whole place was burned.
Really?
There was not 1 inch of that room that was not black from fire. So what's don't overclock, kids? Is the punchline.
Well, when you overclock, you have to get the reasonable gigahertz you're going to overclock. And you have to check the
Well, you're saying overclocking from 600 megahertz to 2.1 gigahertz isn't reasonable?
4 times.
It's fine.
It's not that time is not reasonable.
I mean, the guy lived. All right, let's take about 10 minutes. We'll come back. We'll do our final hour, and I think we're hopefully going to get to the death assignment.